Welcome everyone again. In today's webinar, we are going to talk about energy efficiency of motor-driven systems, how we can identify potential issues, how we can improve the efficiency of the motor-driven systems. Of course, we will start with what is the motor efficiency, what are the common issues that yields to inefficiencies in motor-driven systems, and then we'll look into the signs and symptoms of inefficiencies, and then what type of tools we can use to identify these issues, and then how we address them. And we will close with a couple of cases that we have. And then, of course, we'll have at the end questions and answer sessions, and then we'll try to answer your questions. So let's get started. Okay. One second. Okay. What is motor efficiency? So the motor efficiency is essentially the output power of the motor to the input power, where, of course, the input power to the motor system is the electrical energy, which is then converted to mechanical energy by the motor itself. That's the output shaft power. And of course, along this conversion of energy from the electrical to mechanical, there are losses. And of course, we are trying to minimize these losses, but the ratio of that output power to the input is our efficiency. The higher the efficiency is, the better it is. And this is represented in terms of percentage, right? So thus, understanding motor efficiency is crucial for optimizing energy consumption. So we have to know the efficiency to be able to identify and quantitatively, so that we can reduce and address these issues and reduce the cost of inefficiencies. And this will help us, of course, significantly reduce the operational cost, as well as the inefficiencies effects on the environmental impacts, right? So, and then, if you look at this at a larger scale, in any given plant, you have hundreds and thousands of motors. So any small improvement in the efficiency will help companies to achieve their sustainability goals. And looking at the statistics, as you can see here, 63% of all the electricity used in the industry in the US is consumed by electric motors. So this is putting everything into perspective, that there's a lot of power consumed by the motors. So any small improvements you can see here can make significant contributions to energy savings, again, thus reducing the cost of the electricity, as well as improving the reliability of the asset, and of course help companies achieve sustainability goals by minimizing the carbon emissions. So when we look at the efficiency in formulas, you can see that, as we already mentioned, the output power divided by the input power. So that is our percentage. And of course, if you look at here, the denominator, the output power here is, the efficiency is basically the output power plus the losses, right? So what happens to the energy when it's converted from electrical to mechanical? You get the output speed. But since the system can never become 100% efficient, you're losing the energy. So what happens to that energy? That actually turns into heat, right? So that becomes, copper losses, stator or rotor copper losses, or iron losses, or due to the improper ventilation. Again, the temperature inside the motor gets, higher. So all of this energy will turn into heat. So we are trying to minimize these heat losses. So this is essentially, how the efficiency works in the motor. So when we understand this concept and then, of course, achieve higher efficiency in the motor, we can appreciate and comprehend the importance of motor efficiency and how much it can actually help us to save on the energy side. Looking at these again, the significance, the first and foremost, the effect will be on the reduced operational cost. At the end, you will have less electricity bills. It's as simple as that. And then having using or wasting less power, you will, considering that the most of the power still is generated from traditional sources, you will again help contributing to lowering the gas or carbon emissions to the atmosphere. So this will help, of course, combat the global climate change. But more importantly, if you look at here, less heat on the machine, since it becomes more efficient, it will actually result in longer lifespans and reduced maintenance needs, because when the motor gets hotter, the windings, the lifespan of the windings on the stator will actually decrease significantly. Any 10% increase or in the temperature of the stator windings will actually halve the lifespan of the windings. So then it will turn into more serious problems, and eventually you will risk, motor failures, and then you will have to replace or send the motor for a repair or new windings or rewinding of the stator or rotor issues. So this is also another important reason why we should care about the efficiency and to make sure that the motor is more reliable and it has a longer lifespan and it's more durable. Last but not least, of course, when this is employed or deployed at a larger scale, as a part of maintenance culture, this can actually, again, help the companies become more competitive and adopt more, energy efficiency approaches and lowering operational cost and aligning with more sustainable practices that the companies nowadays are setting to themselves. So, all right, so we will look at the factors that are affecting the motor efficiency. We can have 5 major key considerations here. One is the design of the motor, which is the stator and rotor design, and how how is the quality of the core materials that are used inside and the windings, and how efficiently the winding techniques are in order to minimize, again, the copper or heat losses there. The bearings and the seals that are used in the motor, low friction bearings and effective seals minimize, again, mechanical losses there. So this is basically how efficiently the motor is designed, and as we will see that there are several efficiency classes that internationally accepted. And the second thing is the operation conditions. What are the operating conditions of the motor? One factor is the load, of course. What is the size, if the motor is proper size or not, and if you're running motor under low operating conditions or low load levels, then the motor will become inefficient. Other factors such as the conditions that the motor run in or the contamination, as well as the cooling, will play, again, a key factor in the efficiency or the performance of the motor. Another one is mechanical faults. So when we talk about the efficiency here, actually we are referring not just the motor, but the full system that the motor drives, right? So at the end, the motor converts the electrical energy to the mechanical in order to do some work, right? This could be driving some pumps or fans or compressors or conveyor systems. So if we have inefficiencies on the drivetrain or the driven equipment, this will still become an inefficiency problem. Okay, so mechanical faults will affect, again, the overall performance of that, and we will see the details of this later on. And another factor here is the power supply quality. So, whether the motor is driven by a VFD or transformer, or if you have just a mains So the quality of the power supply will affect the performance of the motor, and of course, these factors will be the voltage quality, voltage imbalance, harmonics, how sinusoidal the output of the voltage signal that is coming to the stator. So these will have significant effect again on the efficiency, performance, as well as reliability of the motor. And last but not least is cooling and thermal management. Again, this essentially goes back to how effectively the thermal management is done inside the motor, and this is related to the design and construction of the motor. So, we mentioned the design and construction. So the International Electrotechnical Commission defines efficiency classes for electric motors based on their efficiency. There are 4 commonly used efficiency classes internationally, and starting with the efficiency class 1 to up to 4, and the efficiencies goes from 91% to 95%. And you might not see these the differences between these classes too big, but considering especially for big size motors, these numbers actually mean a lot, and you can make your, of course, return on investment calculations, but the higher the motor is in size and power, the more meaningful these numbers will be. And then initial investment will be, of course, high for the efficiency class of 4 motor, but calculating the savings just for that additional 4% increase from 1 to 4 will be quite significant, and it might be worth investing into energy efficiency class 3 or 4 motor, especially this will hold true for medium voltage systems. And of course, we will later on look at this again and how easily you can make these calculations with the help of additional tools such as the condition monitoring technologies that we as Artesis offer with the electrical signature analysis approach. So another factor was the operating condition, and as you can see here, that condition is clearly shown here with this chart over here, the efficiency chart of a 110 kilowatt motor. You can see that the efficiency will be maximized between 60 to 80, 90% load, and it will drop significantly below 60% loads, right? So this tells us the importance of proper sizing, and of course having the motor again run within those optimal conditions. And if not, we need to be able to calculate again the cost associated with improper sizing of the motors. But of course, in order to do that, we have to understand this chart and the relationship and how much the efficiency will decrease when the load declines. So and improper sizing, of course, can be done in 2 ways. One is you can either oversize the motor or undersize the motor. We will look at these individually. The other one is, of course, as we have looked at, the mechanical faults or any type of motor faults that happens in the motor will also affect, and this will not only be limited to the motor itself, but again, the transmission, the drivetrain, and the driven equipment. Electrical supply problems, again, fluctuations in voltage, frequency, harmonics can affect the motor performance and reduce the lifespan. So oversized motor, so this is, of course, this means that the motor is oversized for the job that it has to do. So the load is a lot less than what the motor can deliver, which means that the efficiency will be diminished, especially if the load is constantly below 60%. And this will, of course, increase the energy waste and elevated environmental impacts. And also, it is an unnecessary investment. So when you look at it, if you need a 50 kilowatt power and you are using a 100 kilowatt motor, that is an unnecessary investment for that particular job. And of course, that is a one-time loss there. But since you are running this machine constantly at a 50% load, you are actually not utilizing the motor's full efficiency performance. So that is an ongoing constant cost associated with this approach. So you need to make sure that the motor is actually properly sized and it's running at an optimal, or at least close to optimal load values. An undersized motor, this is even a bigger problem, because with an undersized motor, your motor cannot actually meet the demand or the load demand. So it is now running at under stress and trying to work harder to do the same job. And of course, it is consuming more energy than it needs to. And of course, the motor will get hotter and run hotter. So therefore, immediately the motor will actually become more inefficient, because a lot of energy will actually, again, will be converted to heat dissipations. And this heat is, will not just make the motor, again, less efficient, but excessive heat actually reduce the component lifespans, including the stator windings and or other components inside the motor. And potentially, depending on how much additional load is on the motor, it will be actually, it will yield to premature motor failures. So, and of course, when the motor fails, you will have downtimes, and that will also cause additional production losses and potentially, additional operational cost, and you would need to send the motor for repair, or you would have to replace it. So you will also need labor, or there will be labor costs associated with this practice. And last but not least, here is, of course, in extreme cases, excessive heat actually can risk fire. So this is even a bigger problem. So when the motor actually, burns, essentially, then this will be an even bigger problem, and it will create safety risks in any plant or factory environment. So, we have to keep a close eye on the motor's load levels, and then make sure that the overload situations is under control and doesn't happen. If that is an ongoing thing, you have to consider a proper size new motor for that particular job. So now we have looked at the operation condition. Now we're looking at the electrical or mechanical faults, and how are they affecting the efficiency of the motor-driven systems, right? Rotating assets, basically. And as you would know from your condition monitoring or maintenance practices, that there are certain mechanical faults, that can be detected with different approaches, and mostly the focus will be on making sure that the motor is running, and you replace the faulty component inside, and then let the machine run. But not much attention is actually paid to the energy efficiency effects of these type of faults that happens or that occur in rotating assets. So let's start with bearing faults, right? When you have bearing issues, whether it's because of the overload situation, or you have a misalignment or unbalance, improper lubrication, cavitation, which will essentially create frictions, whether these bearings are on the motor or on your pump or fan. These will create frictions, which will cause the motor to consume more energy in order to overcome that friction. So these frictions will reduce the efficiency by up to 0.5%, on rotating assets, and other type of mechanical faults that can happen is rotor faults. Of course, if you have a broken rotor bar, you will have dynamic or static eccentricity, which will affect the performance, the torque of the motor, and of course that will reduce the efficiency of the motor. Same thing will happen with stator or winding related problems, and these faults can actually reduce efficiency by up to 3%. And of course there are different factors that contribute to stator or winding insulation problems, and some of them already have to do with the power supply quality, as we have mentioned here. Other most common mechanical faults would be unbalance and misalignment. In fact, this is almost 50% in low voltage motors. So as you can see here, the efficiency effects of unbalance and misalignment is even higher than bearings and rotors. So and therefore, it is important to monitor these parameters as well to eliminate the efficiency effects of these type of faults. Of course, unbalance and misalignment will happen more often, and so of course with proper balancing techniques or alignments, these can be eliminated. Another one that has the highest effect on the energy efficiency would be belt-driven systems. So then this falls under the transmission category, of course. But if you have a belt-driven system, belt-driven fan, and then you have loose belt or sheave misalignment, that can actually reduce the efficiency up to 5%. So this is quite a significant number. And of course, causes of this problem will be overloading, again, misalignments, bearing faults, or wear and tear on the belts, again, sheave misalignment. So these type of faults, again, will have the highest effect on the energy efficiency, not on the motor side, but if you think at the simple terms, that the motor, so you have the motor inefficiency, so the electrical power converted to mechanical output, and you have the power at the shaft now, but that power from the shaft will be transferred to the fan through the belt. So if you have issues with the belt, that energy will even be lost even more, and that can be up to 5%. So that's significant loss, and so addressing these issues then will become very important. So we have looked into, again, a couple of mechanical faults that can have significant effect on the energy efficiency of the rotating assets and full system. Other problems would be electrical supply problems or power quality or power supply issues. And so we need to also monitor voltage imbalance or over voltage situations, harmonic distortions, phase losses, poor power factor, sags and swells on the voltage, loose wirings, poor connections on the terminals, crest factors, and of course, having a look at the raw waveform itself will help us to see transient peaks in the voltage. So, and how sinusoidal the waveform is. So all this will be important to assess, again, the performance of the motors. And when, of course, you have issues in any of these factors, they will show themselves, with different signs and symptoms. And overheating will be the first one, because, again, inefficiency means more heat dissipation inside the motor. And mechanical problems will, of course, manifest themselves as vibrations. And of course, the vibration can be detected with different technologies, and electrical signature analysis is, of course, one of them. And of course, if the situation is quite severe, you can actually hear noises. And of course, at that point of time, you actually are at the latest stage of the PF curve. And of course, the performance of the machine will be reduced, so this will show itself in slower speed, slower efficiency, And of course, the active power consumption will actually reduce. So keeping track of the power consumption will also tell you that the system becoming less efficient. But of course, all this will require some sort of monitoring technology to be identified. And of course, there are different techniques that you can utilize and deploy in your maintenance practices. Of course, thermography would be one of them to see the thermal energy inside the motor. Vibration analysis can be used to detect mechanical issues. But there is a better approach here, of course, which combines all these into one single solution, which is electrical signature analysis, both giving you mechanical and electrical fault monitoring as well as process fault monitoring, and also energy and power consumption monitoring, which now includes the energy efficiency monitoring as well, which now we are going to see in greater detail. So, of course, as if you have attended the previous webinars that we have done so far, you would note that we are utilizing a model-based electrical signature analysis. This technique is using voltage and currents and combining that with a machine learning approach, so to provide both online continuous monitoring as well as an offline version of it. Will give you a 7-minute snapshot with the handheld device that you're seeing here. But what matters here is that this approach will give you both mechanical condition monitoring, power supply quality monitoring, and also the energy efficiency monitoring of the asset, including over and undersizing of the motors. Since it's constantly monitoring the asset, it can tell you whether this motor has been running in underload or overload conditions for a long time. So let's start off with mechanical condition monitoring. So traditionally, of course, mechanical condition monitoring has been the main focus of maintenance departments, in order to make sure that the machine doesn't fail and it runs, right? As I stated earlier, that not much attention is or consideration is given to the energy efficiency effects of these faults. So with this system, you don't have to, do any calculations or pay attention to it too much, because it's all giving you in a simple format. So you can see here, if you have mechanical faults that was initially there and now it is increasing, you will get an automated fault diagnostic from the system, which will tell you your problem is getting more severe. You have a transmission problem, could be belt looseness or gearbox and unbalance, as well as, the bearing parameter. You can see here it's going up. So this will tell you to look at those mechanical faults individually. So to make sure that the bearing doesn't fail, maybe there's a misalignment, you align that as well. So make sure the machine is running. But also at the same time, you get the information from the system, which will give you the energy efficiency effects of these existing faults here. And in kilowatt hours, you can see this bearing fault causing 500 kilowatt hour per year. And of course, these numbers will change, depending on the size of the motor. But in total, these 3 mechanical faults will cause 6,500 kilowatt hours per year. So that's a significant number. But now, of course, you can say 6,500 kilowatt hour doesn't ring, a much bell, maybe. But when you actually factor in the cost of electricity and enter that number into the system, it will now calculate the cost for you in terms of, US dollar or euro or whatever currency you want to use. So, and then when you see that in terms of, again, dollar or euro, that will make more sense. And then you can make an immediate judgment call to whether to act on this issue right now, so that you eliminate these wastes. And then you can make these calculations on an annual, monthly, or weekly basis. So now, that was the energy efficiency effects of the mechanical faults detected by Artesis electrical signature analysis. Now we are going to look into the electrical power supply quality issues and how this can be monitored with the system, and then what is the cost associated with this in terms of efficiency, right? Now, the system will do live monitoring of all of the electrical parameters necessary to keep track of the power quality, including voltage, current values, power factor, crest factor, harmonic distortions, and current voltage imbalance. Additionally, you will actually see the total energy consumption, not just the efficiency related part, but the consumption hourly, daily, monthly. So, which assets are consuming most energy and what is the total watt, again, on a monthly, daily, or hourly basis. And then these numbers, will be referenced to the rated value of the motor, so then you can immediately see if there is any discrepancy on the measured values, and you will see the total power consumption in terms of, again, dollar or euro, or again, your currency of choice. And the system will also tell you, again, how much you are going to lose if there's any problem with regards to the incoming power quality, right? Let's give you one example to make this more clear. So let's say you have a 100 horsepower motor, and then it had a 1% voltage unbalance, nominal values, and then it went from 1.1% to 2.5. So that's a 1.5% increase in voltage imbalance. This is actually quite significant, because any 1% increase on the voltage imbalance will increase the current imbalance 7 to 10 times more, which will then start affecting the performance of the motor and heat up the stator windings, and again reduce the lifespan of those. But the immediate effect will be reduced efficiency. So you can see here the efficiency will drop from 94.4 to 93. So this is a 1.4% decrease in the efficiency of the motor. And when we make these calculations, assuming that this motor is operating 8,000 hours per year, the annual cost, because of this change only, the voltage imbalance increase, will be $1,500. So, and this is just one parameter, and it's, considering that how much does a 100 horsepower motor cost, you can see that this is actually quite a significant energy waste. By just addressing this issue, you can save $1,500. You can also, calculate this number with the return on investment into condition monitoring systems, so that, not just from again, fault prevention perspective or predictive maintenance perspective, but on the energy efficiency side, this alone, might justify the investment into such systems. So let's look at the over and undersizing suggestions of the Artesis system. So here we have an example of a motor here. So this equipment operates at a load of 126%. So which means this is actually an undersized motor. Normally we generate an alarm if the motor operates at more than 120% of its rated or full load ampere or rated power. So, and here the system will immediately make suggestion. So the reference equipment will be the one that you are currently using, which is not enough for the job. So it will tell you that you have to actually go with a power rated power of 315 kilowatt. And then it will tell you what is the rated efficiency associated with the suggested equipment. And same thing with the oversized motors. So if the motor is oversized, it will tell you again how much efficiency cost that will bring to you, and then it will make the suggestion. From that, this equipment is running at a load of 23%, which means there's almost no load. So, and it's less than 60%. So it will make a new suggestion for you automatically. So this is the rated power you should have for this job, and this is the rated efficiency that the system recommends to you. And all this also will not be just suggestions, but also you will actually see the calculations, the energy usage of the new system, the alternative equipment that the system suggests to you, which will be several different efficiency classes. So our reference equipment was, the 48 kilowatt, the active power consumption, but this is the energy usage. So if you switch from this one to this, you can see that the annual energy consumption will drop 4,000 kilowatt hour per year. So this is given to you here, and the cost savings are here as well. So this is $450 per year saving. And if you go to a higher efficiency motor, you can see that these numbers will be provided. So the system will basically tell you everything you need without making so much calculations. So how much energy savings you can have just properly sizing the motor, and it will also provide the carbon emissions associated with the energy savings. So you can also see the environmental impact that this move will provide to you. Same will apply to, again, undersized motors here. So you go from undersized motor to higher. So this will, again, with the same logic, will tell you the annual cost savings if you move from your reference equipment to a new motor with proper sizing. And then that new size, of course, will have different energy efficiency classes. And then you will see those calculations, made for you here. And then you can make your calculations to, have a proper size motor as well. And the last thing that the system is also providing is, even if your motor is properly sized, what happens when you actually move with the same rated power to a higher efficiency class motor. So this information is also available on a system. So maybe your motor has failed, and this is a 200 kilowatt motor. You want to get a new motor. So the system will tell you what happens if you are moving from a efficiency class 2 motors to 4 or 3. So you can see those calculations here again. And then maybe, you would want to purchase a motor with a higher efficiency class, and assuming that this new motor will maybe run 10, 20 years. So now you can see a tool like this will, again, help see energy efficiency effects of the mechanical faults, not just fault detection. So condition monitoring online, real time, will help you make better informed decisions, as well as will provide you the numbers that you need to make, informed decisions. What is the cost associated with these savings and how much that is in US dollars? So what happens with the efficiency design of the motors, and what happens with the proper sizing, and what happens if you improve the power supply quality. Say we have a transformer, that voltage imbalance went from 1 to 2%, and you want to buy, you want to either fix the issue, if you can, you want to buy a new transformer. So in order to justify that investment, you might want to make these calculations to justify it. So because the savings will outweigh the investment into a new transformer. So, and having a single tool providing you all this information will help, again, your energy efficiency improvement strategies drastically. And so before we close, let's look at 2 cases here to show you some real life cases provided to us by our clients. So here is a case from a pump, a blower from the US. So you can see that this trend on this blower started to go up significantly, and there was loose windings, and you see here the temperature, the loose connections here, the temperature was high. So this system was actually losing efficiency. You can see the active power consumption significantly dropped around the same time this has increased. So a small issue like loose connection here will actually cause that. And you can see that drop in the efficiency and active power consumption was actually, if this was running for a full year, equivalent to $7,000 per year in these motors. And there, so here are the calculations. As you can see here, daily consumption was $110, so yearly consumption would be 14. So that daily consumption, you can see that it actually dropped when the efficiency dropped. So the difference between these two numbers from 42 to 35,000 is almost $7,000. So you were doing less work with more money. So and basically a small fault detection like that will help you to again eliminate unnecessary energy consumption on your systems. And when you look at another example here, so this was actually a misalignment case. Sorry, I missed for the typo here, but it says unbalance. The misalignment happened due to a frozen pump, and then there was a soft foot, and which created misalignment. And here you can see the increase around this time, January 9 and 10. So this is when the increase happened. And around the same time, you can see that the energy consumption, went up from almost 24.5 kilowatt. This is the active power consumption to 26 kilowatts. So, and 1.5 kilowatt almost. So this is 6% increase in the power consumption with the same load levels. So that's a lot because of the soft foot and misalignment. And when you turn these numbers into an annual consumption, of course, that will be a significant number. So, and this is $2,000 energy savings annually for this particular machine. And 20 kilowatt is not a big motor, but if this was 250 kilowatt, then the same consumption would be $18,000, or same waste. So because of course, corrective action, that issue was addressed, and then the energy waste was eliminated. So hope this clarifies and provides more insight to, how this sort of more global approach to rotating assets, both electrical, mechanical, and power quality monitoring, will give you better tools and insight to understand the energy efficiency effects of design, power quality issues, as well as mechanical issues. So we have come to the end of our presentation. If there are any questions, of course, please write them into the chat box, and I'll try to read them and answer them one by one. Okay, QA. So there's a question and answer session on the browser. So if you can type your questions, I'll try to answer them. If they are in the chat box. So far there are no questions, so let's wait for a couple more minutes. If there is none, then we will end our presentation here. If you have questions later on, of course, you can always send your questions to inquiry.artesis.com. So we'll try to get back to you with your individual questions. Yeah. All right. So apparently there are no questions, but yeah, please send your questions to Artesis email address provided here. Okay, there are questions. So there's one question. Are there new features available to existing Artesis equipment? Yes, there are new features coming to the existing EMCM and AMT Pro equipment. These are software updates, which will come free of charge to the equipments. And this efficiency that I just presented will come to the AMT first, and then it will come to the AES software for the EMCM. And there's no hardware requirement, so it will be, compatible with the previous Artesis hardware that you are using. So is there any point where we should use portable or online system? So, I mean, this question, we're getting a lot. So this depends on several factors. I think one is how critical the motor or the asset is for your for your system or for your applications or process. So, we have cases where, people are monitoring very small motors, but it's very critical for their processes. So they cannot bear any unplanned shutdowns or downtimes or failures. But on the other hand, if the other thing is that if the motor itself is medium voltage and very expensive, online continuous monitoring makes more sense. But the portable system can also be used for all the other equipment, that doesn't justify continuous monitoring. So both can be used in the same plant, and they will not compete each other, but actually complement, so that you will have monitoring for all of your asset by using both portable and online system of Artesis. Question is, the efficiency calculations are done by the software? Yes, the efficiency calculations are done by Artesis software, both online as well as the AMT software. So will there be any presentation on the Artesis human interface and report generating capabilities? Not sure if I understand this question. Is there any VFD variable that can be monitored for fault detection? Yes, we are monitoring VFD-driven systems as well. So if there are problems from VFDs, where you have tuning problems or component failures or filter problems, we will be able to detect them, not directly, but by looking into the power quality or raw waveform or crest factor, we will be able to make those analyses. Do you monitor harmonics? Yes, we do monitor harmonics. And the harmonics are both available on both software, both on-premise and on clouds, and that's actually one of the important factors to monitor the incoming power quality. I meant with devices, how can we monitor and improve the harmonics generated from the drives or the motors themselves? Of course, this has to do with the filtering, right? You have to have active or passive filtering. So this system will tell you that there's the problem. The solution to that will vary dependent of the application. But for harmonics, of course, the active filtering is the first one that comes to mind. So another question from Mark, are there any modification to MCC to be done before using portable system? Yes and no. Actually, the short answer is no, because in order to use the portable system, you can just open your MCC panel and use the non-intrusive probes to start doing your test. But if you don't want to open your panel and do live motor testing, you can do so by installing the additional optional plugs that we're providing, which will then sit there permanently, and then you will just use a plug to connect to the MCC to make your live motor testing. So both options are there. Okay, I think there are no more questions, but in case there are. So on the chat box, Leonardo asked, what is the alarm settings for crest factors? So the there are no alarm factors, but we are using standard sort of range, and that depends whether the machine is driven by a VFD or it's a non-VFD driven system. So if it's a line driven system, of course, you don't want your system to exceed 1.6, 1.7 crest factors. But if it's a VFD driven system, a trend comparison is a better approach, and also looking at the raw waveform, what are the transient peaks you see on the sine wave itself. So I hope that answered that question. So let's see what other. So there's a question: easy setup, plug and play device. So for online system, yeah, all you have to do is install into the MCC. You need 3 CT at the current transformer, which will sit there again permanently, and you will make a network connection to either an on-prem switch or you want to go to cloud, you can do that, and then it can be remotely commissioned, and that's it, you're good to go. And in order to commission the unit, all you need is the motor nameplate information, voltage, current, frequency, RPM, and then that's it. So it's an easy setup. You don't have to access to the motor. So that's, of course, one of the most important features of this approach, is that there's no sensors needed on the machine or on the pump or motor. So everything can be monitored from MCC. Of course, most importantly, including mechanical faults, which most people are having a hard time to accept or comprehend, but this is what the system can do. So does AMT Pro has the feature to monitor the harmonics of the motor? Yes. All right, I think that's it for today. There are no more questions, but again, if you have any follow-up questions, please feel free to send them to us, and then we'll get back to you. Thank you, everyone, for again joining into this webinar, and hopefully we'll see you on the next one. Thank you.